Guys, last section we looked at how you transform polynomials. Today we're going to look at more characteristics of this today, and our title is Analyzing Graphs of Polynomial Functions. Question we're trying to answer, how many turning points can the graph of a polynomial function have? When I say turning point, it's like saying it goes from increasing, gets to a top here, and then starts to do what, kids? Decrease. And it gets down to the very bottom from decreasing, then it might start to do what again? We call those points turning points, okay? And we're going to be concerned about where those turning parts are, or those turning points, if you will. We want to know where they are. We want to know how many we have. We want to know what values they have. So guys, goals today. One of them is to use x-intercepts to graph polynomial functions. And again, decimals is going to help us a lot. 2, use the location principle to identify, what's the word? Zeros, roots. You've heard these words before, right? Okay. Of polynomial functions. We're going to find turning points and identify local maximums and local minimums of graphs of polynomial functions. And then the 1, if there's kind of anything that's really somewhat difficult for kids, it's this right here. So, I don't know, you might put a star by this one right here and say, pay attention on that when we get to that part right there. For some reason, that's kind of difficult on kids, but I think that once you see it today, you'll understand what's going on, okay? All right, guys. First vocab term is a local maximum of a polynomial. Anybody want to read that for me?
The y coordinate of a turning point, the local maximum for the function point is higher than all nearby points.
So, it's kind of a turning point. A local maximum, I always call it a peak. All right, so a local maximum is going to be like a peak for us. Okay. So if I had some graphs right here, if I had a graph that did this, where do you think the local maximum is? Very top, okay? It's higher than all the points around it, right? So this point right here, that would represent your local maximum, okay? So if a local maximum is kind of like a peak to a graph, what do you think a local minimum is? Good word for that would be valley. Let me get the door here quickly. Yeah, a good word for that would be what again? Valley. Peaks and valleys, or highs and lows, however you want that to go. I like to call them peaks and valleys. So local minimums are going to be like a valley. It's going to be the y-coordinate of a turning point of the function when the point is lower than all the nearby points. I'm going to draw a graph like this. How many local minimums would this graph have? 2. Does that have a local maximum? Does, doesn't it? But the 2 points I've highlighted, those would be local minimums, wouldn't they? Wouldn't those be local minimums? Okay. All right. Kids, let's talk about even functions. This will be another vocab term that comes up, and we'll look at the examples that come along with these. For now, just understand what the characteristics of them are. Even function. A function f is even when f of negative x equals what? For all x in its domain. The graph of an even function is symmetric about the what? Okay, here's what I want you to know. Even functions, okay? We're going to be given an original function f of x. If f of x is equal to f of, when I input negative x, if those 2 equations, or if those 2 functions are equal to each other, then we consider the function to be what kind of a function? Even, okay? Graphically, if you look at stuff graphically and see this, I don't know what to make. I'll make something that looks kind of like this. Guys, if I folded that right on the y-axis, if I folded that, and I did the best I could to sketch it, I mean, you could get the idea, but is there like a line of symmetry to that?
Yes.
Okay, where is that line of symmetry? Okay. If the y-axis is a line of symmetry to a graph, then that function would be an even function. So I might just highlight right here to say the graph of an even function is symmetric about what? About the y-axis. Okay. All right. Algebraically, f of x equal what? F of negative x. Okay. Graphically, symmetric about which axis? Y-axis. That's what it means to be an even function. Now think about this, guys. We talk about degrees of polynomials all the time now. The only way you can have an even function your degree is what? Even. Okay, and we'll talk about that as we move forward, all right? Odd functions are a little goofy, okay? The big idea behind odd functions is this. You're going to be given a function f of x. It will be odd if, we have to check f of negative x and negative f of x. And we'll look at examples like this here. If those two are equal, then the function is going to be considered odd, okay? Now, odd functions are a little goofy. So the graph of an odd function is symmetric about what? Symmetric about the origin, okay? It says one way to recognize a graph that is symmetric about the origin is that it looks the same after how many degrees of rotation?
180.
Okay, if you can put your finger on the origin and spin the graph half a turn, yes?
I didn't do that.
If you can spin the graph half a turn and it's exactly the same, then it's going to be an odd function. So let me make a sketch of something that would look like an odd function. So on my coordinate plane, if I had a graph that kind of did this, came up, kids, if I can say, okay, here is my point that's the origin. First of all, what point must it have to pass through for sure? It's going to have to pass through the origin. If I could go ahead and pinpoint this point right here and take this polynomial graph right here and make half a turn, would it look exactly the same?
Yeah.
Okay, does that make sense?
Yeah.
Okay, so that would be an example of an odd function. Okay, guys, we've talked about end behavior before. The end behavior of a polynomial function is the behavior of the graph as, it should say x approaches positive infinity or negative infinity. Okay, you remember doing as x approaches infinity, f of x approaches positive infinity or negative infinity. That was probably the first section that we talked about in chapter 3. Okay, so end behaviors are going to come into play. It's going to be something like as x approaches infinity, what does f of x do? And we're also going to look at as x approaches negative infinity. We're going to ask ourselves, what's f of x do again? Or what are the y values do? Okay? All right. Should be done on page 1, I believe. True dat?
Just 1 second.
I'll step away and give you some time. All right, let's go to page 2. Like page 2, it's good stuff here, okay? Kids, not necessarily going to get focused on the graph or anything like this here, but before we get to example 1, we need to understand that anywhere where the graph is increasing, it has what? So if I had a graph that looked like this, I don't know. Okay? If I had a graph that looked like that, where are my positive slopes at? Now again, you read graphs from left to right, don't you? Okay? Well, here's what I tell kids all the time. Mark off the peaks and valleys. Okay? In this graph right here, if I start on the very left, is the graph increasing or decreasing? It's increasing to here. I get to the peak and go to the valley. Is it increasing or decreasing here? Okay, so then what's happening from the valley back to here? Okay, so aren't those the parts on the graph where it's increasing? Okay. Decreasing. Okay, what kind of slopes must they have if they're decreasing? By the way, are these positive slopes? Is this going upward? As I move right, it's moving upward?
Yeah.
Okay. If I draw the same darn graph, and mark off my peak and valley, guys, describe to me where the slopes will be negative, where the graph will be decreasing.
In between both of them.
In between here, right? Here and here, this is where the decreasing part is, right? So we get that, increasing, decreasing. And then we remember what symmetric means, right? Symmetric means you can cut something in half and the left side would mirror the right side. And we typically talk about our symmetry today with respect to the y-axis, okay? All right, let's get started. Kids, first thing it says to do is use x-intercepts to try to graph a polynomial function. Now, I'm going to be honest with you. I think decimals would be a good thing, but here's what I want to point out to you guys. A couple things. First of all, I want you to understand the degree on this function first and why it is the way it is. Okay, if I would set this equal to 0 right here to find x-intercepts, kids, what's 1, 0 that would go in right there? 2. Okay, so I would plot 2. Okay, right there, 2. Then, what's going to go in here?
-3.
A -3 is really getting accounted for how many times here? Twice. Okay, -3 is going to get accounted for twice. Let me ask the question here first. Do you understand the zeros of this first? Okay, now, the question is going to come up. What degree is this function? It's going to come up again. Now, if I would multiply these out, guys, really, this x is getting accounted for how many times? Twice, and then isn't this the third x right here? So if I would go ahead and expand all of this, multiply everything out, we would have x to what power in the end? X to the third, meaning this would be what degree of a function? Okay, I want to kind of talk about this, all right? Some things that are going on, okay? We're going to say the zeros were where again, kids?
2 and -3, -3.
Okay, my -3, I'm going to put this little note right here, dr. That's going to stand for a root that gets accounted for how many times?
Twice.
It's called double root, okay? Now, if you would think about this right here, if I would take this x right here times 2 more x's, this would be x to the third, right? You guys remember the chart that said, gosh, if I have an odd degree function, my graph kind of makes an S on indicators, right? But what about my leading coefficient? Is that positive or is that negative? It's going to be positive. So the graph is going to have to come up here. Okay, now things get kind of funky at double roots right here, guys. If I would put a value in here like so, yeah, I'm just going to do it. I'm going to pick some x values to put in here, and you're going to help me with this graph here. I'm going to show you this in decimals here in a second, and we'll use decimals as a shortcut, but I want you to understand why some things are happening the way they are. So make an XY table like this right here. I'm going to need your all's help today, okay? Let's start at -4. We already know -3 is what value, kids? Yeah, 0, right? Put -2 in. Put -1 in. We know, I want to go up to about 4. So we'll go 0, 1, 2, let's go up to 3. How's that sound? Okay. Guys, we also know at 2 we're going to get what value out here according to our graph. Okay. I need some volunteers to help me. Who's willing to put -4 into the function and get me a value? I'll do -4. What's -4 minus 2? -6. What's -4 plus 3? -1 times itself would be 1. So isn't this 6 times negative? Or isn't this -6 times 1 here?
Yeah, it's -6.
-6 times 1/4 would be -1.5. Okay? Okay, you guys see what I'm doing here? I'm going to go through the rest of the chart quickly, okay? Let's see, -2 would make -4 here. -2 would make that a 1, right? And 1 squared would be 1. So, 1/4 of -4 would be -1. Okay, let me put -1 in here. That'd be -3. This would be 2. -1 plus 3 would be 2. 2 squared would be 4, right? So you're going to end up with -3 here. 0 should be pretty easy, right, guys? What's 0 minus 2? -2. What's 0 plus 3? What's 3 squared? 9 times the -2. -18. And then 1/4 of -18 is -4.5. Okay.
Now it's going to start going back up.
Looks like it, doesn't it? I'm going to plug 1 in there. 1 minus 2 is -1. 1 plus 3 is 4, and 4 squared is 16, right? So I've got negative 16. What's 1/4 of negative 16? Okay, I'll plug 3 in there. I get 36 times 1. I get 9 for this one. Okay, 3 common 9. Okay, let's just plot our points as well as we can. Okay, first one I came up with here, guys, and I know I went quickly through this, but do you guys get my method there? I guess that's the question. Okay, do you understand our zeros right away from what we had up here? This is broken down to x-intercept form, right? Okay, let's plot the first point. Left 4 and down how much, kids? Negative 1.5. We knew negative 3 was 0. What's negative 2? Where is 0 at? Oh, I'm sorry, negative 1 first. And negative 1 at negative 3. Where was your negative, I'm sorry, your 0 was negative 4.5. Negative 4.5 right here. Okay, what's the next point I should plot? 1, negative 4. Okay, then we were at 2, 0, right, guys? And 3 common 9, that would be up here somewhere. Okay. Then your point 3 common 9. Guys, it looks like to me this graph is going to come up, it's going to touch right here, take off this way again, right? Okay, so I'll do the best I can to sketch this graph. How am I doing so far? How did I do? You okay with that? Now, again, is that perfect? No. I want to hone in on one part right here. One part I'm kind of concerned about is this. You guys told me one of the zeros was what? Negative 3. I'm going to highlight this point. Negative 3, 0. That is this point right here. You said this was what kind of a root? A double root. Okay. I want to talk about characteristics of double roots real quickly, kids. When you have a double root like that, a double root will come up, it will just touch the x-axis, but the graph will not cross the x-axis. It'll curve back down to the same side it was on. So, as I start to the left, isn't this approaching the x-axis right here at negative 3? And if it just touches and then stays on that same side, what kind of root are we talking about here? Double root. Okay, let's see if our graph is correct. What do you say? I'm going to need help typing this into decimals. You talk me through this. I know it was 1/4, right? X minus 2 was the first quantity? And then I want to square that, right? Guys, how do we do? Are my roots at negative 3 and at 2? Do you see this idea of a double root right here? Okay, how many times does that negative 3 get accounted for in our equation? And if I'm looking for a root or a 0? Twice. Okay. Again, here's my suggestion. Make your graph, use decimals to not get an answer, but use that to confirm your work, okay? All right, let's take a look at our first example or our second one here. Okay, I love example 2. Okay. A couple ways we could go about this. Locating real zeros of a polynomial function. We could use rational root theorem. You guys are good at rational root theorem, right? I could try splitting this, couldn't I? Okay. You want to hear about your splitting option on this? Not going to work. Okay. Splitting's not going to work, so it looks like rational root theorem would be the only thing that works here, right? Okay. I have a little better idea today since we're analyzing graphs. Say that again, Allie? You agree, Andrew? Graph it. Let's try graphing this and find the zeros. Okay, let's see what happens here. So in this right here, you might make a note. So if we're locating zeros, consider what? Okay, consider decimals here, okay? So let's take a look. I'm going to need help here, kids. What's the function? 4x to the third, okay? Oops, sorry. 4x to the third plus 28x squared
Okay?
minus 18.
Now, kids, again, we've talked about this idea of number of zeros here before. Kids, just looking at this right here. First of all, what degree is this function? So at most, you would have 3 reals, right? Is it possible to have imaginary zeros? Okay, looks like to me the zeros here are at -6, -1.5, and what? 0.5. Okay, so I'm going to say consider using decimals. We would say by decimals, what were our roots here, or what were our zeros? Okay, so I'm going to just jot this down. You guys remind me the values again. So by decimals, the zeros were at x equal, you said -6. X equal -1.5, is that right, guys?
Yep.
And then was it positive 1.5?
No, positive half.
I'm just gonna
Positive
say
half?
right and not
Okay.
do any research. You know, you're responsible.
Okay, show of hands, that's about as straightforward as we can get in this whole chapter, isn't it? I mean, consider everything you've done so far in this chapter. That's about as easy as it gets in this chapter right there, isn't it? Okay. All right, gosh, guys, we're moving right along today. Do you want me to slow down
No.
or keep my foot in the gas? By the way, it's only 93 days until Daytona 500. If anybody cares.
Are you going to it?
I'd love to go. That's on my bucket list, Logan. Someday.
Did you go there before?
I've been to Daytona. I've been to a race there, but it was the July race, and that was back in 1987. I was 12 years old when I went to that race in Daytona. And sadly, I was just down by the racetrack this summer. I was like, my gosh, there should be a race here. I was there 2 weeks before the summer race was down there again. I was like, I should just stay here for 2 weeks, but we had to come home. But I was so excited just to see the track again. Oh, memories. Okay. Fun times, guys, fun times.
When did that get boring?
Oh, good God, no.
4 hours of staying?
Oh, gosh. Logan, I'm gonna tell you this right now. I can understand why people would say that if you're talking about TV. I can understand it. But until you've been to one, then you'll understand why I sit. And plus, I'm an old man too, so I don't really have much of a life. So watching cars go in circles isn't the worst thing in the world. All right, guys, core concept right here. The turning points of a polynomial function. Turning points of polynomial functions. There's some rules. First rule, it says the graph of every polynomial function of degree n has at what? Has at most n minus 1 turning points. Okay, let me give you an example of this right here. We just did one. This graph that we had right here, guys, what degree did we say this function was?
That's true.
3. Okay, by that core concept, it says if my degree is 3, then at most I can have one less than the degree turning points, okay? So what's the most number of turning points I could possibly have in this? How many turning points did we have? There's one peak and one valley right here, right? Okay, so if I've got a 17th degree function, what's the most number of turning points it can have? Does that mean it has 16, or is that saying that's the most it can have? 16 or less. Okay, so that's one rule about points right here that we're talking about in this core concept. Okay? Secondly, if a polynomial function has n distinct real zeros, so like the last one we looked at had how many zeros? If you have 3 for sure real zeros, then its graph has exactly n minus 1 turning points. So if I look back at decimals right here, that graph right there had how many real zeros? 3 of them, which means that it definitely has how many turning points then? Does this appear to have 2 turning points, kids? So here's the deal. I have a function with 7 real zeros. It must have how many turning points? 6. Okay? All right, so let's take a look at what's going on here. Okay? It says example 3 has turning points. The first thing we're looking to do, what's it say? Find your x-intercepts and the points that are local maximums and minimums. Determine the intervals for which each function is increasing or decreasing. There's a lot of stuff going on this right here. Make sure you pay attention. Okay, first of all, what's the degree, kids?
3,
So at most, how many turning points? 2. Okay, let's see how many real zeros we find. Anybody want to read that function for me?
x to the third minus 2x squared plus x minus 2.
Whoa. Looks to me like this only has...
I think you have to zoom in a little bit.
Looks like me like it has only how many zeros, kids? 1 real zero, right? Okay. I'm going to read something again.
Person, what would you do if somebody, like a student, bought you 2 extra days off?
I would go. If a polynomial function has n distinct real zeros, then its graph has exactly n minus 1 turning points. I'm not sure that's true. Distinct. Okay. These aren't distinct, so that's okay. All right, so here's the deal, kids. What's the zero on this?
2.
2, okay? Do we have a minimum and do we have a maximum? Okay? Let's answer the questions here first. All right, so let me go back to this. What's the first thing we had to find? Find the what?
X-intercept.
Okay, the x-intercept. So I'm going to just text box this for you. All right, so do this. Get a decent sized up there. Okay. The zeros were just what, kids?
2.
Okay, now we have to ask ourselves, where's the minimum at? Local minimum, I should write. Let's go back to our graph and look at the local minimum. So a local minimum, is that a peak or a valley? What's that point?
1, -2.
Okay, so I would say that local minimum is at 1, -2, so the value of that local minimum is -2. We also have a local maximum in that, don't we? What did it say our local maximum was here, guys, at the top? 1/3, comma. So is it okay if I put that in 0.333? I wish I could control and copy those all the time. Okay, so can you guys remember -1.852 for me?
I got it written down.
-1 point, what was it, 852?
8, 5.
Okay, what else are we asked to find here, guys? Determine the intervals for which the function is increasing or what? Okay, this is the part that I get worried about. I want to talk about increasing parts and decreasing parts. Okay, here's what I suggest you do when you're working on finding increasing and decreasing parts. Okay, do this for me. I think it works well to do your peaks and valleys. Okay, now what I like to do with this, and I'm not telling you have to do this, but I like to do this. I like to put in my x equals at the peaks and valleys. So I'm going to put in x equals 0.333 like we did here. And then I'm also going to put in x equals, what was it, 1, -2 for the minimum? So the x value on 1, I'm sorry, yeah, it's 1, -2, right? I'm going to put in x equals 1. I like to look at this stuff in terms of intervals. So guys, take a look here. This purple line is x equals 1, isn't it? To the left of 1, is my graph increasing or decreasing? So I would say my graph is increasing for x values. Actually, this is the 0.333 line, right?
Oh, yeah.
So this would be it's increasing for x values less than what, kids?
0.3.
Okay, so let's go write that in there. So it's increasing for x values less than, whoops, for x less than 0.333. That's one place. Is there anywhere else where it's increasing? So here's 1, and after 1, doesn't it start increasing again, kids? Guys agree it starts increasing right there? So how would I describe where it's increasing there? And for x values greater than 1, right? Okay, talk to me about where it's decreasing then, kids. So it's like an interval. It's the between part, right? So we write those intervals. Yep, so we would write this as 0.333 is less than x. Because this is kind of like saying we need x values. This is kind of like saying we need x values bigger than 0.333. But less than what, kids? And that's how you would write that, okay? How you guys feel about that? Pretty okay with that? Okay, let's try another one here, all right?
You need to keep that up.
Yep, I will. Okay, am I any more time there?
Just give her a second. I got it.
Okay. So right here, let's do that again. Clean these up. New function. I know it starts x to the 4th. Can you help me with the rest? Plus 2x. Ooh, this is a cool one. What degree is this function? 4th degree, isn't it? So how many real zeros do I actually have here? Ooh, this is going to get fun. Why don't you guys write your zeros down first there?
Those are all,
How would you have liked to have found
all
those
terrible.
values? Oh, I missed one, didn't I?
Those are all bad.
Or no, that's this one right here, isn't it?
Good lord.
Okay, negative 1 point. Thank goodness for decimals,
Do
right,
we
guys?
have to?
They're all bad.
Whoa. And then I'm going to go into decimals and write this down again, so you guys are going to tell me what they are. Let me know when you've got them down. I'm going to copy this real quickly.
Well, there's also you know that.
Gosh darn it, that's not going to work.
Can you just like highlight it all at the top?
I thought I could, but I tried and it didn't work. It didn't. Let's try this here then. Okay. You guys ready for zeros for me?
Yeah. Negative 1.113 0.
Okay, next one.
0.244. 1.821 and 4.048.
Okay. Then we need the local mins and local maxes. So minimums would be at a peak, right? Or I'm sorry, a valley, right? So let me get these zeros out of here again. Let's get the zeros out. And I'm gonna, you guys know how to squeeze this, don't you? Hit shift and then just kinda, Just hold shift down and pinch that like so. So these are local minimums, right? Ay, ay, ay. Write those down for your local minimums. You guys have your 2 local minimums down?
No.
Okay. When somebody has it, let me know, and then we'll put it on the document, and you can get them from that.
Some people just pencil way back.
You want that maximum right now? Okay, who's got something written down they can read back to me? Allie, you want to do that for me, buddy?
Sure.
Okay, so help me out. What were your local minimum coordinates? What was the first one?
Negative 0.574, comma, negative 4.879,
Okay,
and then 3.254, and then negative 14.949.
okay, and then we had a local max, didn't we? Just one?
Yeah.
And that was
1.07, 4.035,
comma 4 point.
035.
Okay, now we gotta look at some increasing stuff, right? Okay, and I'm gonna write this down. I'm gonna do some writing on our graph here, so give me a second. You can write these down as I, whoops. Okay, let's go back to the graph here. Let's just take a little snapshot of this. I'm gonna put, do you guys like the vertical lines in there? Do you see it better that way? Okay, I'm gonna put them in there then. So what was the minimum down here on the left, kids? X equaled, so negative 0.574. Okay, what was the maximum at? X equaled 1 point. Okay, and then what was the other minimum at? X equaled.
3.254.
Okay, this helps me a lot see what's going on when I put those lines through those peaks and valleys. So let's talk right here. I'm going to write on this one. So, guys, it looks like on this, if I go, so this is left of this blue line, right? Okay, is this graph increasing or decreasing right here? Decreasing, right? So you're going to go to your decreasing part in your notes. Gosh darn it, what's going on here? There we go. You're going to say X is decreasing. I'm going to put decreasing because that's what we had first, right? Or did we have increasing? Was increasing up top on your notes?
Yeah.
Okay, I'll do it this way. All right, so let's talk. So it's decreasing to start. This is X left of what value here?
Negative 0.54 is our.
So for X values less than negative 0.547. Okay, I'm gonna kind of put my increasing ones up top here, so I'll draw a line between them. Is that okay, guys? Okay, what's happening between here and here? The blue line and the green line. So that's increasing from negative 0.574. Whoops. Negative 0.574 less than X less than, what's this X value right here for the green line? Was that 1.07? Are we good there? Guys, I'm between the green line and the purple line now. Increasing or decreasing? So it's decreasing, and you'll write this down in your notes, decreasing from 1.07 to, what was this X value again on the purple line?
3.254.
3.254, so it's decreasing from between 1.07, so I write it as 1.07 less than X, less than, you said 3.254? Okay, are you guys writing these down in that note section part? And then the last part is to the right of the purple line. Right of the purple line, are we increasing or decreasing, friends? We are increasing, right? So if I'm increasing from here to here, that's going to be increasing for x values greater than 3 point.
254.
A lot of writing there, isn't it? Okay. Kids, as far as the characteristics go, where the zeros are we okay with that? Where the maximums and minimums are we okay with that?
Yeah.
Is it easy to identify that stuff in decimals?
Yeah.
When I'm looking for increasing and decreasing parts, I encourage you to put those vertical lines in there and then look at them as certain intervals to determine am I increasing or decreasing from here to here, okay? Guys, I think I'm going to stop there today. We'll probably, let me see, example 4 is my last one, right? Yeah, I'm going to stop there. We'll look at those last 3 tomorrow. So, guys,